Hello, my dear friends. This is Dr. Mohamed Nezami again, coming to you from Jerash, Jordan. Um, I welcome you back to my series on the design of K and Ka band SATCOM low noise block down converter or a front end receiver for Ka band SATCOM. Well, this is part six, so we're still going. If you recall, just so that we remind you back, um, I've started this series way back, and we've got part one, part two online. This is my YouTube channel. I would urge you, please, this is the address. I would urge you to, or just look me up, just say Mohammed Nizami YouTube channel, and it will get you here. But you can see that the series that I've started here is part one, part two, part 3A, part 3B, part four, part five, and today we're going to have part six. Okay. Now, last time, well, just to remind you, just a little advertisement. I'm a freelance RF and microwave designer, world level designer. Um, I work remotely. Mainly primarily for clients in the US and Europe, some in the Middle East, some in India, some in Asia, Singapore. I design things anywhere from DC to 35 gigahertz. I work with you on the specifications or requirements, build specifications on system architecture, verify system architecture via System View and MATLAB and so on. And then do actual circuit schematics and layout. And as an example, this is a KU band LNB that I built for somebody, a treble band. As you can see, there's three synthesizers on here. So please, if you have some work to be contracted offshore from the US and Europe, feel free to contact me. This is my email, and my number is on the website as well. And you can check my LinkedIn page also. You can get to me from there. The first consultation is always free for the first few hours. I basically turn in the whole design to you, just a BCB and BCBA fab files. I work with you on selecting the parts. I do all these. Anyway, so let's get back to our Ka band LNB. This is the block diagram that I've got right now for the Ka LNB that we've been designing. If we can go back to here, we can go back to System View. This was designed with the LNA in here specified with these top level specifications, namely 30 dB gain, noise figure of sub 1 dB, and then you got the saturation level is 13 dBm. Okay, so the LNB itself is a dual band. So we've got dual image rejection filter. We come in here, we switch between them, and two dual LOs. Okay, and then of course we have a common IF stage in here for both, and that's why we switch between two LNBs, is because we want to maintain the same IF to shift back the IF into the same band. I have designed this, refer back to part one and two. That's where we analyze this, and you can go back and check all this stuff. So this was designed back then, and if you look at the budget link analysis in here, so we've got these, let's see, this is the desired channel power, the cumulative gain, the cumulative noise figure, the output P1 dB compression point throughout the whole chain. And this is right now is programmed for this is for the low band, okay? And this is what we've got. So we verified all the system level, and I have designed the filters last time, of course. Now recall back that we have this is the frequency plan that we had. Basically, we had two bands from 17.2 to 21.2, and we chopped them into two bands, two LOs and two IFs. Okay, I mean common IF, sorry, for both of them. All right, so today we have designed these filters. Okay, all of these are selected mimics and ceramics, and we're gonna last time in this part last time part 5, I have started the design of the low noise amplifier, which is 30 dB low noise that includes the waveguide to microstrip transition or the probe. And this is the design for the waveguide to BCB transition. As you can see, there's a probe that is going inside here. Okay, you can see that the substrate goes in, but it doesn't have a ground plane. And then I have a little suction of a quarter wavelength in here that will match the impedance of this probe to a 50 ohm line on a substrate. That's Roger 4003, 8 mils height. Okay, so what we're going to do today, we're continuing this process. So this is what we still got to do. The low noise amplifier, finish that design, and to finish the microstrip to waveguide. All right, so LNA design, here we go. Okay, top specifications, like I said from last time, this is what we use in the block diagram. So this is what we're gonna do. We selected the device. Here's the device. It has a gain of about at 21 gigahertz. It has a gain about roughly 11.5 dB. And the noise figure is about 0.6 dB, noise figure minimum. So we need 3 stages of this amplifier to be designed. And we worked last time. We got I got the small signal model in here, the S parameters 3520. This is the device. And then I designed the system based on this. I still are waiting to get access to the nonlinear model, which will enable me to generate S parameters at various bias points other than the single bias point, which NEC or CEL have given out here, okay? And that way I can predict what the saturation level and what the 1 dB compression point is at third order insert. Okay, so how do we design this? Well, classically, we just followed exactly the same theory that is detailed in this book here. The microwave transistor amplifier from Guillermo Gonzalez, Miami University. And by the way, that's I did my PhD at Florida Atlantic University in Boca Raton, and that's only 40 minutes away from Mr. Gonzalez in here. And when I took amplifier design at Florida Atlantic University in my PhD days back in the 1990s, I used an earlier copy of this book, okay? This is a great book if you don't have it. So we got the device, and all we need to do now is we need to match it to 50 ohm in here and 50 ohm in here. The only difference is that we need to match it on the input side, we don't match for maximum gain or maximum power transfer. We really have to pick the gamma opt, which gives you the minimum noise figure. And in part 5 in here, that's what I did. I showed how you pick that point by plotting the noise figure circles by this command here for ADS, and then the gain circles by this command in here, okay? So last time, this was the design that I came up with. So I've got the transistors right here. I've got a stabilizing resistor and bypassed by a capacitor in here. Okay, and then I've got another section in here to ground. So we've got a series and a parallel stabilizing circuitry components for the amplifier. This is the output match, which is basically to match the 50 ohm to the conjugate of S22 of this network in here, this combined here, which encompasses the transistor and the R and quarter wave section at 20 gigahertz, and this RC here. And on the input side, the gamma opt to match to the gamma opt was just using a single open stub like this. And of course, why I use single stubs that are open, not short, I will show you momentarily. We do that because we have to insert negative voltage bias on the gate and positive voltage on the drain. So in that case, then we can't really have, we don't want to use DC decoupling from the match section. So that's why we use open, not short. So the response for this circuit in here using ideal transmission line components is this here, which is nice. It fulfilled the gain and fulfilled the noise figure, which is nice. And then, of course, if you cascade three of these, that's what I did here is I just copied this entire circuit in here three times. One time here, one time here, and another time in here. And when you run it, you get precisely here it is, you get anywhere from 32.6 dB gain to down to 30 dB. So, which is really nice. And the noise figure is also maintained below 1 dB, which is good. Of course, the match on the output, we are very well matched, very good, acceptable S22. But on the input, of course, we are not. And this is really normal. That's what you usually do. If you have a low noise amplifier, you can really never see a low noise amplifier that has return loss somewhere better than, I would say, sometimes 7 dB, 6 dB. That's because we really need to have a low noise figure, and that, as I showed in last time, the optimal point on the Smith chart for gamma opt is a way further away. It's not the same location as the gamma of the device itself. So we need to match for not maximum power or maximum gain, but for noise figure. And you can check back, please check back to the other one. Okay, so what we're going to do, we're going to take this circuit in here, and then substitute transmission lines to these. So what we're going to do is, I go back to my ADS. So we started out with this here. Okay, so this is the transistor, and these are resistors, even though they're not plotted as resistors, but right now it's a two-port network. This resistor is from, whose resistor is this? Let's see. That's a CH series, and it is from, I'll check it back in a minute, but this is a thin film resistor that is appropriate for Ka bands, okay? So what we want to do is we want to replace these lines with real transmission lines, and the way we do that is we go to the tools and we get the link cap, line cap, and then what we do is we just basically program it so we can do this. Like for instance, in here, let's see, this line is 30 ohm. So we got 30 ohm. It's already programmed for this. 141 ohm. And then we synthesize that. So the substrate is RO 4003, 8 mil height. And when we run this, of course, it will solve and give you exactly the width of this line should be 36. And the length is 134. Okay. And you keep going to all of these. So what we're going to do, we're going to close this and go to the actual. Okay, so this one is this is it here. So if you open this is basically right here. You can see that these lines has been replaced by microstrip line, which is specified with a certain width and a certain length, and the substrate, which is M sub 1, and M sub 1 is specified in here. So we do this for all of them. The components, the cap components, I already selected. This is AVX cap, high Q caps, and this is AVX cap. The resistors I've selected before, okay? And the quarter wave line in here was selected as well. So now what we do is we run this, and we hope that it will not deviate a whole lot from the actual ideal lines, okay? All right, let me check what's going on here. Okay. Okay, so let's see it now. So we've got, like I said, we're at this single stage using no, this is three stages. Let's see. This one in here is the LNA that we have designed, single stage. And we said that the response of this is really acceptable and nice and everything. And so we're going to take this now and replace all of these lines with actual lines. And we have this cap is already chosen from AVX. We need also to put a bypass cap, a DC decoupling cap on the output. So let's see. Now all the lines have been replaced by their equivalent from ideal to real lines, and the capacitors have added this cap in here. So now if we run this, and ta-da, this is exactly what we got. So we're still good that we don't have the noise figure is 0.6, 0.7. That's what we got. Okay? And that's was the actual substrate lines, and the gain is anywhere between 10 to 12. So we got 2 dB. So what we're going to do next is we're going to use 3 stages of this and see what we get. So let's see. We're going to get 3 stages in here. So what I did is I took the same section, I copied it 3 times, okay? And let's run this and see what we get. And hopefully that's not going to be very far from the actual one with ideal lines. And that's what we got. So we got the noise figure is still at most now we increased 1/10 of a dB, so 0.8 in here. Okay. And the gain is 36, 35, 33 in here. So we have a slope that is sagging in here. And remember, this is still, now I don't have any optimization on this. I have not ran any optimizers on this. This is straight forward from last time. So what do we need next? Well, what we need next is to get let's go back here. So we did this with actual lines, real lines, 3 stages with real transmission lines, and that's what we got. We ran that. And now what we need to do, we need to do biasing. We need to add the DC bias, because this topology in here, right here, now still missing the drain bias, which we have to add right here, and then the gate bias, which we have here. And like I mentioned in the part 5, I can't afford having DC decoupling on the input. The input to the waveguide is actually going to be a probe, an open circuit probe, which will have DC on it, so that I don't have to face, because I want to preserve the input in here without any components that would enhance or introduce thermal more thermal noise than I could that I would. Okay. All right. So we're going to add a drain bias and the gate bias. And if you recall from last time, for the device that we have chosen, the 3520 NEC, the point of bias that we want to run it at is 10 milliamps. This is the bottom of the ball right here. And to get 10 milliamps of this, if you look at the IDS versus drain source current versus voltage gate to source current, which is negative, the 10 milliamp in here, you would need to introduce at the gate about 0.43 volts, negative volts, okay? So that's what we're going to do. And I took this as an example, a textbook example. I think this is out of Gonzalez's book. I'm not sure, but I took it from this site in here. Thank you. I like to recognize the source in here. But this is a generic misfit, PHEMT, FET, gas fit bias. That is, they all have the same topology. First of all, we have the input side. This here doesn't have any input or output matching circuits. So all it has is a DC isolation DC blocks on both sides. So here's the drain in here, okay, and here's the gate. And the way we introduce this, we get the negative voltage and we go in and we have some kind of circuitry in here. And what it is basically, the first thing we do is we decouple, we bypass for medium frequencies, low frequency stuff, ripples on the negative supply, because a lot of times this one here usually comes from an IC that takes in positive voltage and creates, it's an inverter chip that creates a negative voltage. And this has a switching frequency on it. So you don't want that. You want to isolate that from the gate. Otherwise, it will modulate it and it will distort your data, incoming data. So, and then we have an RF choke, okay? And then we have a split resistor divider in here. And the reason we have this is because a lot of times this is like -4 volts and we want to get -0.4 volts. So we use precision resistor divider to get that gate voltage to us. And then what we need to isolate the DC supply from the main line. And the way to do this, okay, we can't use an RF choke like this at these frequencies, at millimeter frequencies. But what we have here, we have right here, we have a quarter wave line in here, high impedance quarter wave line. And that quarter wave line, as you know from prior videos that we have on this, if it's shorted at this point, it is shorted quarter wavelength line. And you know that a quarter wave line transformer, as we might call them, basically inverts the impedance. So if it's short, if the load is short, it would look like open on this side. And that's precisely what we want. We want the looking into the incoming signal in here at Ka band, we want it to see open in here, because we don't want any loading from the DC biasing section. And we have another open quarter wave line in here. And the reason we do this is because we want, at this point, we want a ground short. And the way we short it also, again, we short it virtually with a stop like this, quarter wave stop, open. If it's open quarter wave, then at that particular frequency where it's quarter wavelength, it will be, at this point, it'll be short. And short at this point will make this quarter wave line section look open from here, okay? And this is an explanation of what these components are usually for. And the same thing we do on the drain. It's exactly precisely the same, except in here, we don't have a voltage divider. And in my case, I may have one, okay? Because you need 2 volts for my case. We need to bias it at 2 volts, okay? At 2 volts, okay? And to do that from a voltage regulator, a 3-volt voltage regulator, you still need to split that. Okay, so we're going to design a small section of DC bias at the drain and at the gate for this, okay? So this is the topology that we're going to follow, which is a standard. And here it is, okay? So what I did in here, basically, the only difference I didn't use a rectangular open stop. I used radial stop. And you can check back one of my videos. I did introduce radial stops. And, okay, right here, these videos in here. I introduced, here it is. Okay, so this is here. You can see that this whole video was talking about radial stops on the drain or source. Okay, so you can check. But essentially what I want, okay, I have used a little 5 mil line sections and 10 mil section on here, and this is a T junction, okay, and then this is the quarter wavelength at 20 gigahertz, okay, and this is also in the middle in here, it's a quarter wavelength. And it will get less and less as we go on both sides, okay? And this is just to introduce broadband open stop, okay? So essentially, in theory, what will happen at 20 gigahertz, this point here, because it's open stop, it's going to look short. That short right here is going to short this quarter wavelength. And this quarter wavelength, of course, from on the other side, it'll be open. And then the signal that comes from here goes out to here, none of the signal will flow in here, okay? The rest of this is just basically you can check back on, just type on Google DC bias for gas fit amplifiers, and I will explain all of these to you. Okay, so if you look at the frequency response from here to here, it's going to have this shape basically. At a certain resonance frequency, the resonance where this is a quarter wavelength, and this is a quarter wavelength, it will look completely open this way, and you will get minimal loss. And you're going to get like this, okay? And that's what you really get, okay? So meaning it doesn't have any impact, very little loss introduced. So, okay, now this is, of course, with ideal components. So what I did is I went on and replaced these with actual transmission lines and these with actual capacitors and inductors and resistors from manufacturers. And that's what I did in here. Every one of these components is from a manufacturer. And when you run it now, suppose theoretically it should give you the same as this, except, of course, here the Q is infinite for these components. So what's going to happen is you're not going to get a sharp resonance like this. And that's precisely what happened. So, okay. And of course, the resonance will move because of the prosthetics interaction with the actual components. It's going to shift the resonance center frequency of this. So you're going to have to do a little tuning. It's about 19.3 gigahertz right now. So we have to, in this case, what we have to do is we want to increase the resonance, so we shorten the length of this and the length of that. And I'm going to leave that for my optimization, which is going to come next. Okay, so let's get back to here to ADS. So we're going to go in here and introduce. Okay, so we're going to go to bias circuit. The bias circuit is right here. You can see there's the quarter wavelength radial stop and this one. Radial stop basically get it from, there's a menu in here for microstrip lines. Let's see, T lines, microstrip. Okay, and here it is. You can get it from here, right here. Okay, so you just go in here and you just pick one. Okay, and you specify the parameters. So let's run this. And we run this, and that's what we're going to get, basically, okay? And you can see that the resonance of this is basically at M9 and M9, 20.5 gigahertz. So we need to shift it back a little bit. But anyway, this is, right now, this is from ideal components. These components are all ideal. So we're going to replace these components with actual components, actual model components that contains S parameters based on measured for the inductor. You can see this one here is from a Coilcraft, and for all these parts from various manufacturers. So, and of course the packages is all 0402 packages, really tiny. Okay, so I'm going to run this, and of course, you're going to get the same thing in here. Okay, there it is. And you're basically, if you look at the resonance frequency, it's 19.3. Okay, so you need to increase it a little bit. But it's perfect, so it doesn't have any loss that is significant. So it's just basically 0.1 dB of insertion loss. Okay. All right, so we got this going. Now we have to go back to the amplifier and introduce it into the amplifier circuit. So, and this is it. So we got the amplifier in here. This is the same amplifier. There's a transistor device. There's the input matching, and there's the output matching to transmission lines. There's a stabilization circuit. Oh, what is this guy doing here? Okay, and there's the stabilization parallel circuit in here, okay, with real components. So what we did, I added both the, here's the drain bias, and here's the gate bias. And what I did instead of DC, I put an input, because I want, sometimes what you want to do is you want to sweep, this is an input, and this is an output, to see how much isolation you get between these. Okay, so we're going to run this. And basically, this is what we got. So now the gain is still about 10 dB. Okay, 10, 11, 10 throughout the band. The return loss on the input output is still the same. It didn't vary a whole lot. Of course, the significant thing is that the noise figure, we want to see what happened, and it did changed. Now we're up to 0.9 dB. 0.9 dB, so we're still not very far from 1 dB. And here's the input and output return loss for the whole amplifier. Okay, so now let's leave this. And now I'm going to copy this circuit 3 times and see what the gate, what is the gain. So we've got 3 sections in here. Here it is. I copied it this time in here. Here's one. Another time, and here's another time. All of this is 3 stages. Now remember, when I designed a single cell here, I designed for 50 ohms. So theoretically, all you have to do is just cut and paste forever. Okay. And in my case, I needed just three stages. And here's the final response without optimization, of course. So we've got the gain is 32, 33 almost in here, 34, 35 dB and 35 dB. So you can see the gain is very flat in here, okay? And the return loss is you can see here, the worst one is now the output, of course, it got degraded a little bit. Okay, so we need to have this below, say, about -8 dB. The noise figure, which is the very critical, is still 0.98. We're just barely touching the 1 dB in here at the higher frequency. And that's understandable because at higher frequency, you get more loss on the input side. So now we want to do next, okay? Some people, so I have, this is a 3-stage amplifier, okay? That is working fine and good. What I want to do now is prototype it. So this is ready. Now all of these sections in here, so you can do BCB from ADS, but I don't want to do that because I want to build this in a totally different environment for schematics and BCB, which I use Cadence in this case, Allegro and schematic capture from Cadence. So what we want to do next, let's see what so we got this. Okay, we got this is 3 times. Okay, where we are. Okay, so what I'm going to do next is, here's what I'm going to do. In my schematics, which I will draw totally in a separate software package, okay? Some people, what they do is they design this completely BCB right here, and they just glue it into there. But I don't want to do that. I actually want, what I'm going to do is leave all of this stuff that is all these passive components. I want to leave it. But what I want to do, I want to make a sub-circuit out of the output bias, everything that involves precise microstrip lines. I'm going to make a circuit out of this on the input and the output, which includes the drain bias with the output matching, and then the gate bias circuit with the gate input matching. And I'm going to basically create a footprint and export it and use it in my Allegro. And that's basically what we're going to do next. So what happened is I got this. So what I did is I constructed the input and output sections, okay, right here. And what I'm going to do is I'm going to create a footprint so that I could export just the transmission line stuff in here, okay? And so I did that, and basically this is what I got. Now, unfortunately, I only realized this at this point that the output matching, I use a low impedance line here, 30 ohm impedance line, and that seems too wide, so I don't like that. So I'm going to go back and redo the matching section of the output later on. But what I do is you take this here and you make it a 3-terminal device, sub-circuit, and basically export it to from ADS, okay, as a Gerber file, if you like, to so here's the input on the side, okay, and so if you do this, this is I did this, and I want to ignore all of these passives because I'm going to reconstruct this in schematics And then what I'm going to do is I'm going to only export the microstrip work. Okay. So if you go to layout on this, create a layout just so that you can, okay. So this is basically, this is my microstrip work. Okay. So basically I want to take this here. I want to take this here, and I'm going to take all of this and okay. So this piece here, I'm going to ignore all of the other passives. I don't care about it. So this piece here, I'm going to go ahead and export this. And let me see if this would work. I didn't try this, but we're going to export it as a Gerber, for instance. Here, a Gerber drill. Okay. So, and I'm going to view it. Okay. So I'm going to say, okay. Okay, here we go. So this is my Gerber of this. This stuff in here, this is the passives. I'm not going to worry about this. I'm going to go back and erase them, but this is what you would get. And that's what I'm going to take into my other, the full schematics. And of course, we do the same thing to the output matching section. Okay. So that's what we got. So this is really puts now, okay, so now somebody might come in and say, wait a minute, this is this amplifier in here. What about the verification of all of this stuff? This stuff in here, as you can see, the DC theory-wise, all of this stuff in here is short anyway. This point in here is short. So you really, this here, theoretically, it's not supposed to interact at all with your RF. So what you're doing when you export just portions of this just has to do with the drain bias microstrip line section and the output and input matching. That's totally perfect. So what I'm going to do is do that, and then of course what I will do is we will revisit when I do this in the Allegro layout. After layout, of course, I'm going to export this back into ADS and do what we call, you can go to my videos in here, these videos in here, that will show you how you do post layout performance verification. Okay, you can really check right here, which is what I did here. Okay, what this will do, it will utilize the basically it's the same. We take this circuit in here, okay, the three stages, which let's go back to it. So we take this here, and then what will happen is this, all of this will be an artwork, copper work with input and output ports. And we're going to bring back this copper that's going to be laid out here, and then bring in these components, the equivalent of these components, and the transistor itself, okay? And then we're going to run it by simulating combined S parameter and EM finite element method as computed, and it will give us what we call post layout verification, okay? All right, so we're done really with the low noise amplifier. So what's next? Well, let's go back to the rectangular waveguide to microstrip line. So what we have in here, this is the same substrate. It's a Rogers material substrate. Let's go back to, I just pull this up here. Okay, so we're going to go back to, as you can see, Rogers 4003. And this substrate in here, so the design of this, also I covered this in my other videos. There are some other videos that I did cover the microwave waveguide to microstrip line transitions. You can refer back to these. And so what I did is I designed this right now. And so what we're going to do is we're going to take the S parameters output of this. The frequency response of this is this, basically. So we've got, this is the through transmission. and this is the reflection for the lowest waveguide mode, TE10. And this is for this one here, for the the second mode, TE20. And let me see, make it 5 so that you can see it here. Okay, so that's this guy in here. Okay, so what I did in here is I specified for the excitation on the input that I need 2 modes for this. Okay, and that's what happened. So I excited 2 modes in here and ran this, and this was designed. So this is a rectangular waveguide. The rectangular waveguide is a standard waveguide for KU band. So if you look at the dimensions of this, which is 10.668 millimeter by 4.318 millimeter, which is the WR, what is it, 25 or 75? I forgot, but so that's what you get. And what will happen is the LNB will be an extension of this here, basically. So what I did is I came in here, and let me just explain it a little better on this. So no, I want it on the side, front. Okay. So what I did right now is this port. This is a board in here that extends through a little cut in the waveguide at a distance from the short end, which is a quarter wavelength in the at 20 gigahertz. Okay. So this distance in here is a quarter wavelength at 20 gigahertz, and what I have is a probe that is sitting right here into the waveguide. Okay. You can see on this side. Let's go to the top and just show you. Okay, so this is the probe. It's going in here. Okay, and then I have this is a 50 ohm line in here. This line in here. So this is a 16 mil wide line, and then between the probe and the 50 ohm line, there is a quarter wavelength transformer, which basically transforms the probe impedance to the 50 ohm impedance. Okay, and let's see if you want to. Let's see. I want to animate this here. How is the work done at 20 gigahertz? How it works? So basically, the wave propagates from here, goes in, and then it will go back. Any signal that goes to this side will be reflected back and totally picked by the probe. And the probe then, basically, we go from TE mode to TEM TQ mod using the microstrip section in here. My LNB is going to be fed. Let me stop this. And let me, okay. So what I'm going to do, this board in here is going to be extended like this, and my LNB will be right here, basically. Now, and that's what we get. Okay. So what do we do now? So what I'm going to do is as a final way of verifying the overall system, what I'm going to do, I'm going to come in here where I used to inject the signal in here into the LNB. I'm going to replace this one here with real parameters from this amplifier in here, from this 3 stages. This is a 3-stage LNA. So I'm going to bring in the S parameters and the linear model of this and put it right here. And I'm going to add another block in here for the transition, which is this one here. So I'm going to bring in here this here, and the performance of this, as you can see, the loss is barely 0.2 dB. Let's see what it is in the middle. So here's one. M6 is 0.11. Okay, and but we're gonna have more than this because of the surface roughness for the copper. Okay, so what I'm gonna do is put it right here. Put the actual S parameters from ADS in here, export them to here. And then what I want to see is what happened to this here. So we're going to go and look at the conversion gain. We're going to look at the also go back and look at the noise figure and gain plot basically for the sweep the input and output. Okay, so ladies and gentlemen, basically this is it for this session, and this is part 6 of the LNB, K band LNB, and I'll look forward to see you in the next section, which will be basically we have to finally just bring in the S parameters, export the S parameters from HFSS, ANSYS HFSS, and ADS into the system view to see the overall for this system, how it behaves. And then we still got the IF section, which has to be designed. Okay, the IF section, which was designed here and simulated here separately in here, we need to see how that behaves. Okay, and the components are already selected, but we need to model it into ADS if we can, to include all the nonlinearities and all the parasitics to verify for that. Okay, ladies and gentlemen, so this is Mohamed Nezami coming to you from Jerash, Jordan. Again, I hope you enjoy this. If you have any questions, please don't hesitate to email me here or call me at this number. This is now for those of you overseas. If you don't have a calling number, you could always call me with your app phone, these phone apps like Telegram and WhatsApp. Okay. So if you have a project that you need somebody to work on for rapid developments, please don't hesitate to reach out to me. I will definitely be of help to you. Well, I appreciate you coming from the ancient Roman city of Jerash, Jordan. To you, I thank you all for the video. Keep liking my videos and keep sharing them. I would appreciate it. Thank you very much. Have a great day. Bye.